Hello everyone, I want to present a collection of common polar curves that you will encounter in a calculus class. Okay, so let's get started on this first one that's really common, which is the circle. Okay, so as you can see, the equation is actually a simple equation, which is r equals some number here. And I set it as a slider on decimals, and as you can see that this a sub 1 is equal to 1 right now. So the circle is centered at the origin and it has a radius of 1, as you can see, right? Because the center is 0 and then the circumference of the circle is at it's hitting the x-axis right here at 1. So the radius is 1. And as you start adjusting this a sub 1 right here, then you can see that the radius will change. And so whatever this a1 is, that's your radius. Okay, so let's just click the play button, and then we'll see that the circle will start increasing or decreasing depending on which side that the slider is going, right? So let's just play it. Okay, so as you can see that it's getting smaller, and yeah, so if it can actually go in the negative direction, and then you're still going to get a circle, and the radius is actually if you have a negative number for a1, then the radius for the circle will be the absolute value of this number. Okay, so as you can see here, you can go all the way to -5, and then the radius is 5. Okay, so that's the first one that you would encounter that's really often. Okay, so now let's look at the other one. Now the other one is a shifted circle, and so let's just look at the equation first. This equation has the form of r equals some number, right, some constant, and then times the trig function cosine theta. And so what really happened is that I can actually change this number, and this number will actually affect the size of the circle. And so yeah, let me show the circle first. Right now I'm setting this number to be at 1, this a sub 2, and when it's at a sub 1, then you can see why the circle is being put right here. Why is the circle being put right here? It's really because when you start with the angle 0, when you put in your lower bound for this function, then do you see for this curve? Do you see what's going on here? If you plug the 0 in here, cosine 0 is 1. And so if cosine 0 is 1, then you are going to get this point, and then you start tracing the circle. And actually, you only need to go up to pi to trace the full circle. And yeah, so again, as we adjust this number, as we change this number, then the size of the circle will change, as you can see here. So if I do it manually, then you can see that, okay, so it's getting larger because I'm increasing this number. And as you can see here, if a sub 2 is equal to 2, so that means the number in front of the cosine is equal to 2. Then do you see what's going on here? We have the circle hitting 2 on the x-axis. And actually, if you look at the radius, it's just what? It's just 1. And so that makes us think that the radius can just be half of this number. But just to verify our claim, then we should actually try some other numbers. Let's say we go up to 3 and see what's going on. Okay, so we go up to 3. Yeah, so 3 right now. So you can see that it's going to hit the 3, and then the other side of the circle is actually always staying at the origin, as you can see right here. So do you see what's going on here? The center of the circle is actually at 1.5 and then 0. And so if you look at the radius, this is 1.5. So that's actually half of this number. Okay, so let's try just another one. If you go up to 5, then you can see that we are going to hit the 5 on the x-axis, and our center would be 2.5. So yeah, so again, the radius is just half of this whatever number that you are having here if the number is positive. And then now you may say, what about if this number is a negative number? And we can actually try that, right? So let's go on the other side. So right now it's 0, and then actually for small values, then it's really hard to see the circle unless I zoom in, but I'm not going to zoom in right now because I still need to do the other curves. And as you can see here, the circle will show up on the other side of the y-axis when you go in the negative direction. So in this case, if you get a negative number in front of the cosine theta, we are going to get the circle on the left side of the y-axis. And yes, so regarding the radius, you are going to get let me use -4 as an example. You are going to get the radius to be half of the absolute value of this negative number here. So in this case, if you take the absolute value of the -4, you're going to get 2. And then that, I mean, you're going to get you're going to get +4, and then you divide by 2, then you're going to get 2. So that's our radius. Is that okay? So for the cosine function, then you are going to get a circle that's either on the right side of the y-axis or on the left side of the y-axis. Okay. Okay, let's look at the other one. This time we are going to look at the one with the sine function instead of the cosine function. And yeah, so if I show it, then you can see that the circle is actually shifted from the origin away, and then it's 1 unit upward. So again, the domain for the data is actually just the same thing. It's from 0 to pi, then you trace the full circle. And yes, so just like before, if you adjust this number, then the circle will get larger or smaller depending on which direction that you're going. And once you go on the negative side of this a sub 3 in front of the sine data, then you can see that the circle will actually go below the x-axis. Okay, the radius is still found the same way. Right now you put 0 here, then the function is just 0, so that's why you don't see any circle on there. Okay, so next one is a spiral. I actually love spirals very much. And if you look at this spiral right here, so yeah, so it's 0.01 right now. So the number is really small. So you can see a red dot right here, but you're not seeing much, right? Let me just put the play button here. One more thing before I do that is that, do you see this upper bound right here for the domain? I actually set it to be this number, so that's why it's not showing the curve. But if I start adjusting this data right here, then it will start changing, and then you are going to get a spiral generated as we play. Okay, so it's being generated slowly, so you are moving in the counterclockwise direction, and then now we'll just keep tracing. And then the reason for why you're getting a spiral is really because when you increase this angle theta, what happened is that you're also increasing the r at the same time because r is equal to theta. And so what happened is that it's going to get larger each time you increase the theta. So as the angle gets larger, then you are going to get a longer, you're going to get a farther distance away from the origin. So eventually, if we go all the way to the 10 that I set, then you are going to generate a really nice spiral. See that looks beautiful. Okay, now let's look at the other one. The other one is another common one that you will see in a lot of the calculus textbooks, and this one is called a cardioid. And so it has a hot shape. That's why it's called cardioid. I have two types right here. So let's look at the first type. The one with the cosine function right here. So let me just show it. This one is a typical one. When I set the a sub 5 to be, actually, let me just set it to be 1 so that you have the one that will show up on the right side. But of course, some portion of it will also show up on the left side of the y-axis. Okay, so as you can see here, we get a cardioid shape, and then if you look at it as a sideways, then it looks like a heart right here. And to generate this curve in general, we got to go from 0 to 2 pi to generate the complete curves. So if you change the domain, right, so let's say you type in pi in there, then you only can generate half the curve. Now let's go back to the full curve right here. And yeah, so adjusting this number will actually make the cardioid larger. So as you can see here. And then actually, let me just stop at 3 right now. Okay, so let's pay attention to some of the intercepts. And for the x-intercept, so one of the points would be a 0. Okay, the other point would be a 6. And then you may be wondering, why are we getting this number 6 right here, right? Just imagine that if this number is a 3, then what happened is that when you plug in the 0 into the cosine data, then you're going to get 1. Cosine 0 is 1. So 1 plus 1, you get 2. 2 times the 3, then you're going to get the 6. That's how we can get the 6 right here. And do you see what's going on here with the y-intercepts? You are going to get positive 3 and negative 3 for this. And as you adjust this number to a whole number, then you can actually see, let's go all the way to the 5, then you can see that the intercepts would actually be 5 and -5 for the y-intercept. Okay, so that's the cardioid with the cosine data. And yeah, so I still need to show you what happens when a sub 5 is a negative number. It will actually show in the other direction, so it's a reflection here, right? So as you can see here, but the other features are almost the same thing, right? You can actually just play with this one. Oh, by the way, I will actually um, post the link. I will actually post a link on in the description, so you can actually play with this. And then I will probably be adding more curves in the future. Okay, so now let's look at the other one. The other one is actually, let's look at this. This one has a sign, and so once you pick a negative number right here, you actually will get the heart shape. So see that it looks like a heart, right? So that's why we call it a cardioid, and it's actually a good curve for Valentine's Day, right? So that's good. Yeah. So you look at this one. If you go in the positive direction, then yes. So a sub 6, if it's a positive number, then you are going to get the one that's the heart is upside down, but then it will go above the x-axis for most part of the curve. Okay. Okay. So next one is a flower. Flowers are nice. They're beautiful curves. And yeah, so if you just look at this, it's actually um, you have a number other than 1 in front of the data for the cosine or the sine function, depending on which one that you're looking at. Right now, I'm just choosing a cosine function. And then you may say, what about the 5? The 5 actually doesn't really matter here. I'm just choosing this 5 to scale the size of the flower. So now, um, for example, if I change this number to a smaller number like 3, then the size of the flower will be smaller. I'm choosing this 5 here just for us to see it more easily. Okay. Um, the other thing I want to mention here is that, okay, so as you can see here, this flower has 4 petals, right? In this case right here, I'm going to just talk about how to get an even number of petals. In this case, we'll be getting like 4. Okay. And then that's really due to whatever it's based on this number n in front of the data. And so what happened is that if this number right here is even, then you are going to get an even number of petals. So like for example, if n is equal to 2, then you are going to get 4 petals. And so the number of petals is actually the double the amount of this n value right here. So you look at the next value right here, then if you go, yeah, so 4, right? I just stop. I actually set the step for this to be 2. So each time it will go by even number. And what happened is that if you just look at this, it's n equals 4. And then how many petals do we get? We are getting 8 petals in here. So the flower actually gets even more beautiful right now. Okay, now if you just go one more, then 6. You see that how many petals do we have? We are having double the amount of 6, which is 12. And if you don't believe me, then you can just count it, right? So you can just count that one. And actually, we can just keep going. And then more petals that we are going to generate. And when we get n equals 10 right here, we are going to get how many petals? 20 petals on together. Yeah. Okay. So that's nice. If you look at the odd number, let's say, yeah, so I'm not using sine for the function. Right now, I'm just going to just look at the cosine. The sine is really just a rotation of the flower. What happened is that this n value right here, I'm using n2 because I don't want to have a variable conflict with the other curve. So for this one, I set that n sub 2 is equal to 3. And so in that case, I'm going to get 3 petals right here for this flower. Okay, and then you may say, why aren't we doubling it, right? For odd numbers, we are not going to double the number of petals. So whatever number that you have right here, then you are having that many petals. For example, if you go into the next odd number, which is 5, then you are going to get 5 petals here. Go into the next one, 7 petals here, and then you can go all the way to 11. Then you are going to get 11 petals. Okay. Yeah, so that's how you can get that form. It's how you can get a flower. The next one, it's an interesting one. This one is called a Limaçon with an inner loop. And so it has the form of the equation that looks like this. You can actually change it to sine, and then you can also change those numbers. The way that you can get an inner loop is that you need to make sure that this number in front of the cosine is greater than the other number that you have right here. So if I change it to like a 5, then you also will still get a larger inner loop. But if you get a 2 right here, you get a smaller inner loop. And then let's say 1.2 right here, then you can hardly see it. But then let me just go back to the 3. What if I change this number to a 2? I still get a small inner loop here because those two values are closer to each other. If I get a 3 here, my inner loop is gone. I get a cardioid. This is actually the same form as the cardioid equation, as you can see here. Actually, let me just look at that here. So you compare the two equations. Imagine that you factor out the 3, then you are going to get 1 plus some 1 plus the cosine theta, which is the same form as this equation. That's why you're getting a cardioid. Let's say if you just go a larger number like a 4, then see that there are no more inner loops when this constant right here is greater than the coefficient of the cosine function. Yeah. Okay, let's just go back to this. Yeah, so that's another one that another common one that you will see in calculus class. And then lastly, it's something that you won't see in your calculus class, but it's nice. And yeah, so tomorrow is Valentine's Day, right? And that's why I'm posting this one. And just want to show you that, okay, so that's how we generate the heart curve. And if you look at this equation, it's actually a really simple equation with absolute value that will generate this curve. And actually, to generate this heart, you only need to go from 0 to pi. And in fact, if you go from 0 to 2 pi, then you're going to generate the other heart that's below the x-axis. That's reflected from the heart at the top. Okay, now let's keep this heart. And that looks nice, right? I think so far I haven't seen any other ones that look as nice as this heart right here. And if you want to fill in the heart, you can actually change this equation into an inequality, which will be even nicer. So then see that we can actually shade the inside. Okay, is that good? And then yeah, so this is the last curve, and I do this just want to show you a survey of polar curves. And the last one, of course, is just to wish you to have a happy Valentine's Day. Okay, thank you for watching this video. See you next time.